Hi everyone, welcome to Netcom channel. So today we will be seeing more concepts in OSPF neighbor and adjacency, OSPF states, and OSPF tables, membership tables. So before going to the concept, we'll be seeing the OSPF terms. What are the packet types in OSPF? What is OSPF neighbor and what is neighbor adjacency? Then OSPF flow diagram, states flow diagram, OSPF states, and OSPF tables. Coming to the OSPF terms, starting with router ID. A router ID in OSPF is a 32-bit unsigned integer that uniquely identifies a router in an autonomous system. A router ID is used by some of the protocols like OSPF and BGP, which is used to exchange routing information between autonomous systems. A router ID must be unique within an area, but routers in different areas can have duplicate router ID. And the next, router priority. It's a value that determines which router becomes the designated router and the backup designated router on a network. The router with highest priority is selected. And if multiple routers have the same priority, the router with the highest router ID is selected. The priority range is from 0 to 255 with 1 as the default. If a router with a priority of 0, it's not eligible to participate in the DR and BDR election process. And the next is the DR, which we call it as designated router, which is required in the broadcast multi-access networks. And we'll be seeing the OSPF networks in the next session. And this DR is needed for OSPF to reduce the wide number of adjacencies and LSA flooding in a multi-access network. And the BDR is the backup designated router. When the DR fails, the BDR takes the role of DR. And with respect to the DR selection, the election boards are hello packets. Each router sends the DR elected by itself in a hello packet to all other routers. If two routers on the network declare themselves as a DR, the router with the higher router priority wins. If router priorities are the same, the router with the highest router ID wins. And with respect to database descriptor packets, link state acknowledgement, link state request, and link state update we'll be seeing in the upcoming slides. OSPF packet types. So we have 5 types of packet types in OSPF, and they are hello packet, DBD, which we call it as database descriptor packet, LSR, link state request, LSU, link state update, and LSAC. And the hello packet, starting with hello packet, this packet is used for neighbor discovery to form neighbor adjacencies and maintain them. And the next one is the database descriptor packets, which is used to check if the link state database between the two routers are identical. It contains the summary of the link state database. Adjacency is formed when both the routers have the same link state information. And the LSR is the link state request packets that request specific link information from an OSPF neighbor. LSU is the link state update packets which are sent to the other router when it receives the link state request. So the specific requested link information will be sent to the OSPF neighbor. And the LS act is used to acknowledge once it receives the update. So these are the important packets which are used in OSPF in order to form neighborship and adjacency. What is OSPF neighbor and adjacency? OSPF neighbor is formed in the two-way state, and the routers in full state are considered adjacent. So let's see what happens in different states. OSPF adjacency is a relationship formed between the neighboring routers for the purpose of exchanging the routing information. The difference between the OSPF neighbor and the adjacency is more advanced form of neighborship that involves sharing routing information. In order to form adjacencies, the OSPF router need to go through 7 states, and they are down, init, two-way, extart, exchange, loading, and full. So this diagram shows the type of states that should be formed in order to become fully adjacent. So when the link between the router comes up, it comes the down state. Down state doesn't mean the physical interfaces are down. It means the adjacency has not formed. Consider router 1 with router ID 1.1.1.1, router 2 2.2.2.2, and in the initializing state, which we call it as init state, hello packet is seen only one direction, where the router ID of R1 is seen on the router 2, but the router ID 2.2.2.2 of router 2 is not sent. It's not seen on the R1. So this we call it as init state. And in the two-way state, hello packet seen in both the directions. Router R1, router ID 1.1.1.1 will be seen in R2, and router ID 2.2.2.2 is seen in R1. And in this state, DR election happens. And the next comes the extart state. Here, the master-slave relationship established. Master-slave relationship is nothing but a session forms between the two routers where the router with highest router ID becomes the master and the other router becomes a slave. And the router that forms as a master will initialize, and it will send the DPD packets to the other router. It will start. And in the external state, the DPD packets are sent, and in the loading state, link state request, link state update, link state act packs are sent. And in the full state, both routers are fully adjacent and database are fully synchronized. So let's go through the states, OSPF states, which we explained in the previous diagram. So in the down state, no hello packets have been received on this interface. It doesn't mean the interface is physically down. OSPF adjacency has not started yet. In init state, hello packets have been received from the other router. In two-way, both the routers have received the hello packets from the other routers, and the bidirectional connectivity is established. And in extant state, null DBDs are exchanged, master and slave elections takes place, and the router with highest router ID will become the master and the other becomes slave. The election decides which router sends its DBD first. And in the exchange state, the actual DBDs are exchanged. And then comes the loading state. In this state, link state request, link state update, and link state acknowledgement are exchanged. So when a router receives a DBD from the other router, it compares the contents with its own DBD. If the received DBD is more updated than its own DBD, then the router will send the link state request to other router about the missing link information. The other router replies with the link state update, and in turn to this, the router replies with the link state patch. So if a router requires a specific piece of information, then it will send the link state request. And the other router will receive the corresponding update to the OSPF neighbor. And in the full state, all the information are synchronized and OSPF routing will begin after the full state. And we have three important tables where the OSPF process maintains, and they are neighborship table, topology table, and routing table. Neighbor table, it contains a list of all neighboring routers, all the OSPF formed networks will be present in the neighborship table. And the topology table, it contains the all possible routes to all networks within the area. And the routing table, it contains the best route for each node network. So these are the three important tables the OSPF maintained throughout its process. So we have come to the conclusion, and if you like the video, please like and subscribe to my channel. Thank you.